Hi there, my name is Micah Wade, and this is my presentation on organic solar cells. The sun produces more energy in just 1 second than all of humanity has ever consumed for all time. And it's just amazing to me how much energy the sun is constantly releasing. It's enormous. Did you know that a 100 mile by 100 mile plot of land, if you covered that with solar panels and you put that in Nevada, that would be creating enough electricity to power all of the United States? That's a quote from Elon Musk. He also says that if you covered a 1 mile by 1 mile stretch of land in the same corner just with lithium ion batteries, that would be enough. Those battery packs would be enough to store the energy that America needs overnight for when the sun is not shining. This would be a pretty bad way of doing it, because people in Florida or people in Maine would need transmission lines thousands of miles long, and that's just not going to fly. It makes a lot more sense to produce the energy much closer to where it ends up getting used. But this simple example really illustrates just how tiny of an amount of land that you would really need to pull this off, because Nevada does really get a lot of sunlight. Okay, silicon versus organic. This presentation is about organic solar, but to understand the benefits of organic, it's good to have some context about silicon solar panel photovoltaics. Okay, so I live in Portland, Oregon, and we have OMSI, the Oregon Museum of Science and Industry. I went there and took some pictures. And to make a traditional solar panel, you start with sand, which is primarily silicon. You purify that silicon and you melt it down. You melt it down and you draw out a single crystal section. This section, this ingot, is trimmed, and you then slice your ingot to make the wafers. These wafers are then coated using processes of doping, diffusion, photovoltaics, and thin film deposition. They are coated to create a solar panel. This solar cell, they get placed in parallel and series to form a functioning solar panel. The solar panels themselves also get placed in series and parallel to help send power to the grid. Okay, so the premise for organic photovoltaics is, imagine if you didn't need to do any of that. You didn't need to have ultra purified silicon, which needs to be at least 99.9999% pure. Imagine if you didn't need any big vat of lava, if you didn't need any of the expensive photolithography semiconductor equipment. Wouldn't that be nice? Okay, getting into the organic side of things, we're going to talk about fullerenes for a little bit. Fullerenes are organic materials. These organic chemicals are compounds found by, discovered by Buckminster Fuller, and he was really into these geodesic domes, which have a similar geometric shape to the actual chemicals that he studied. A lot like a soccer ball, a lot like the Epcot Center at Disney World. PCBM is an electron accepting material. You can put it in a solution and print it for a solar cell. And P3HT is an electron donor. Organic electrodes, we use these to cover the organic solar cell. Organic solar cells are really a lot like making a sandwich. You have your bread, those are your electrodes, and then the peanut butter and jelly inside. Your donor and acceptor material is the peanut butter and jelly. But these electrodes are often either silver or indium tin oxide or P.PSS. P.PSS stands for polyethylene dioxythiophene polystyrene sulfonate, which is quite a mouthful because it's this massively complicated organic molecule. This P.PSS, it's lower cost, it's more flexible, literally flexible for printing on a sheet of plastic and bending it, and it's more available than indium tin oxide. So, which is better? Having a thicker film, considered to be greater than 100 nanometers. This is better for light absorption. You absorb more light, therefore you create more electricity, ideally. All things being equal, if you can absorb more light, that's going to improve the efficiency of your solar panel. But thinner can also be better. Thinner happens to be better for conductivity. Why is this? This seems counterintuitive, especially when you consider Ohm's law. According to the macroscopic Ohm's law, this is Ohm's law, V equals IR, but the R for the resistivity is resistivity equals bulk conductivity times your length divided by your cross-sectional area. So this is the length and this is your cross-sectional area. And if we're talking about a thin sheet that we make even thinner, that effectively means that your cross-sectional area decreases. And if your area decreases, that increases your resistance. But understand, this is the macroscopic Ohm's law, not microscopic, not quantum level. When you talk about the quantum level, quantum confinement on the nanometer level, that's when things behave differently than you might expect. With electron confinement, we are confining to 2 dimensions. And so our equations behave a little bit differently. I barely understand this myself, but in the bulk 3-dimensional case, the world we live in, you have your x direction, your y direction, and your z direction. And you have bulk energy in all of these 3 directions from your electrons. But when you confine it, you decrease the energy because you only have 2 main directions. So here's a video to help us understand a little more.
So the question is, why do nanomaterials behave so strangely? In the case of the nano ice cream scoop, the behavioral change happens when you start to make a material so tiny that its electrons are squeezed into a space smaller than they prefer. It's called quantum confinement.
The smaller you make the crystal, the higher the energy of the electron will be. Its kinetic energy is increased, and that can be thought of as making its wavelength a bit shorter and forcing it into a box where it kind of zips around more quickly.
Just to look at another slide from that video, this initial one with the spinning colors, this is shown because these are just nothing special, just different sized particles. But the size of these particles actually affects their wavelength. And that is partially because of quantum confinement. We'll see that in this slide. The following slides we talk about bulk, 2-dimensional, 1-dimensional nanowires, and quote-unquote 0-dimensional quantum dots. This is a bulk dimensional, just a hunk of copper. This is a thin film organic solar panel. These are nanowires used in a transistor at Intel. P.S. I work at Intel. I'm very proud of that. I'm a technician there. And these are quantum dots. You might have seen these in Walmart or Best Buy. Quantum dot televisions. Depending on the size of the particle, you can control the color. I don't understand how most of these work, but the idea is that by taking away increasing levels of dimensions, starting with 3-dimensional, going down to 2-dimensional thin films, going down to 1-dimensional nanowires, and 0-dimensional quantum dots, you can increasingly confine your electrons so that they behave differently. And this is why the 100 nanometers is really the sweet spot, where you have decent light absorption and you have good electrical conductivity because of your quantum confinement in the 2D case. So, working with tandem solar cells. Tandem solar cells, I said earlier that a plain, ordinary organic solar cell is like making a sandwich. Well, making a tandem solar cell is like making a double-decker sandwich, where we have our bottom device that targets lower wavelength, higher energy, such as ultraviolet sources of light, ultraviolet or perhaps visible wavelengths. We have a top device that targets infrared light with higher wavelengths, higher wavelengths and lower energy. So the light comes in through this transparent electrode, it hits the bottom device, and ultraviolet light gets absorbed and used by this solar panel. However, infrared light passes through both the initial electrode, the bottom device, and the intermediate layer to the top device, which is tuned to target infrared light and absorb that and use that, since all of our light that we receive from the sun is on a spectrum. Okay, this is a group that actually made a tandem solar cell. They made it in 2018 and it has a 17.3% efficiency. They used, for their double-decker sandwich, indium tin oxide as the transparent electrode, PSS as their intermediate electrode, and silver as the top electrode. You'll notice in the slide earlier that since the light is coming in here, it doesn't matter so much. Once the light gets to the silver, it doesn't need to go any further. So silver does not need to be transparent for that top electrode. This is just further illustrating how our upper device can be capturing the higher wavelengths of light, and then the infrared light can pass through to our bottom device to be captured. This tandem solar cell can make for a higher efficiency solar panel. Okay, stability. A solar cell is essentially useless if it can't last long. Things like photodegradation, chemical degradation, air exposure, water exposure can really decrease the longevity of the solar cell. And this is a big drawback that they have compared to traditional silicon photovoltaics. Talking about roll-to-roll processing, this, on the other hand, is one of the main strengths of organic solar cells. This research group showed how they can manufacture organic solar cells with roll-to-roll processing using these big plastic sheets and continuous manufacturing to manufacture these solar cells. And it has the potential to be much cheaper than with silicon photovoltaics. Right now, silicon photovoltaics has a cost of about 20 to 40 cents per watt for the actual solar panel. Organic solar cells are made with roll-to-roll processing and are between 50 and 20 cents per watt today. Many people believe that with economies of scale, right now you go on Amazon, you search photovoltaic solar cell, you're not going to find organic solar cells very much. Most of the time, over 90% of the time, you're going to find silicon photovoltaics are commonly available. These are made with economies of scale. These are the primary photovoltaics that are being made. If you're working with an organic solar cell, you have a much higher initial cost because you don't have the advantage of economies of scale. Okay, so talking about the history of solar power here in America, this is from that report that Dr. Green shared in the first week of class. We see that solar has been experiencing exponential growth during this time. Since 2010, solar power and wind, both of them, have really skyrocketed in the past. And this is largely because of the falling cost of solar power. we see that as solar power becomes cheaper and cheaper, the installed capacity becomes greater and greater exponentially, which is fantastic. But it's still important to note that the current installed capacity of solar power in the United States is less than 1% of the energy that gets used. The vast majority still is not renewable energy, let alone solar. Okay, my conclusions and predictions. This is a current chart showing the majority of the research that has occurred between 1975 and present day. The top area in purple we see are some of the best solar cells, the fancy ones, the 3-junction ones. The plain blue ones are single crystal silicon cells, and these orange ones down here are the organic solar cells, mostly. What do we notice? We notice that typically organic solar cells, even though they've been improving in efficiency, have always had a lower efficiency than traditional silicon solar cells. And to be honest, the goal of organic solar cells is not to be more efficient than silicon solar cells. The goal is to have a lower cost per watt. If your goal is to put your solar cells and power a satellite, I do not recommend organic solar cells. It costs thousands of dollars for every pound that gets sent into space. And if you're going to be powering a satellite, you want to be using the best solar cells that money can buy, the most efficient ones. However, with economies of scale and when you don't have limited space, maybe there is a real future here for organic solar cells. When you talk about massive projects like covering the Sahara Desert or covering a 100-mile by 100-mile portion of Nevada with solar panels, why haven't those things been done yet? It's because it would be so expensive. But if you could use a method like this, which is potentially much cheaper than solar panels made of silicon, maybe people would be more likely to pursue this. And I think it deserves more research today. Thank you. These are my references, more references, and these are my questions for you. Please fill in the blank. The sun emits more energy in one blank than humanity has used in all of our recorded history. A, second. B, minute. C, day. D, year. What is special about this organic solar cell that has an efficiency of 17.3%? Other than good efficiency, what is special about this solar cell? Thank you so much.